Topic 3, Lesson 1. Your notes start on page 49. So your notes start on page 49. So we're not going to be doing as many videos. We want you to use the interactive reader as much as possible. So if you want to hear about this part, go to the interactive reader because there's 2 videos today. I'm just going to talk about some of the other ones. Now on this one right here, I also talk about the other one in the other video about how to use it, domain and range. If you click on this button right here, it will tell you and it will define the definitions for relation, function, domain, and range. And you're going to want to use that left-hand column on page 50 in order to write those definitions. So if you haven't watched that video yet, go out and do that because it's going to give you those definitions. Okay? Identify the domain and range of each function. So on here, what we're doing, this is where you're going to try it in your book on page 50. And your x values are going to be your domain. So my domain, I use my squiggly bracket, 2, 3, 4, 5, and 6. And that's my domain. My range would be 0, 1, 2, 3, 4. Now over here, still have the domain would be your x values, -3, -1, 1, 3, and 4. My range would be 1, 3, -2, 2, and 6. We usually put these in order from smallest to largest, so I would recommend on this one that you rewrite it to actually be -2, 1, 2, 3, and 6. Now, it didn't show up here, but what you need to remember, when I write my domain and range, I don't repeat the values. So let's say that my x values were 1, 2, 2, 5. Okay? My y values were 3, 3, 3, and 8. Then my domain would be written as 1, 2, 5. Range would be 3 and 8. Now, while we're here, let's talk about, is this a function? Well, 2 of my x values repeat. So no, I don't have one input for exactly one output. Okay, good. A function can model each situation. What is a reasonable domain and range of each one? And what this is talking about, reasonable and realistic kind of are the same thing. So I have, and the other thing you need to look at is what's going to be your x and what's going to be your y. So this is 10 gallons per minute. Go back to what you learned in 7th grade math. This is your y, your constant of proportionality over your x. Okay, so it's always y over x. So your domain matches up with your x values. So your domain is the number of minutes. Okay, so I could have 0 minutes. I could have even a half a minute. I could have 3/4 of a minute. I could have 7.5 minutes. So this is going to be all real numbers. And we'll talk more about that in just a second. Your range is going to go, talking about the number of gallons. Okay, so what's going to happen here is that you're going to have gallons. Again, those can be in any numbers. You're going to start from 0, but here you have a restriction. You have a constraint. It's going to go from 0 to 10,000, and it can be real numbers, meaning that it can be decimals and fractions. Okay? A restaurant needs to order chairs for its tables. One table can accommodate 4 chairs. So we're talking about tables. That's my domain. Because the tables is going to make a difference. However many tables, the chairs are going to be dependent on that. Okay, so let's just stop for 1 second. One of the other things that we want to talk about is independent and dependent variables. Dependent. Okay? Independent, those are going to be your x values. And those don't depend on anything else. These are just independent. You decide those. Can choose anything. Within reason, okay? So we couldn't have a negative for if I'm talking about gallons. Can choose any numbers. The dependent variable, those are going to be your y values. And guess what they're dependent on? They depend on what the x value is. Depends on the X value, because that's what you're plugging in. That's the input. So your independent are going to be your input. Notice everything is in. So input, here it's output. Poor dependent variable. It just gets stuck with whatever happens to the independent variable. So my domain here is talking about tables. Well, how many tables can I have? Well, I can have 0 tables. I can have up to whatever would fit in the room. Fits, okay, in the room. But can I have a portion of a table? No. So this would have to be whole numbers. I don't want to say integers because integers means you could have negative. If I'm talking about range, I'm talking about the chairs. And on this one, they're very specific, and they're saying, if I order a table, I'm going to have 4 chairs at it. So this is going to be 0, then 4, then 8, and then multiples of 4. And it's going to depend on how many tables I have. So whatever I stop at with tables, that's what I'm going to stop here. This one has to be a whole number, okay? These all have to be whole numbers. I can't have a portion of a chair or a table. Which brings up continuous and discrete. And that's what we were referring to. If you have a continuous domain, then that means it can be all real numbers. In other words, it can be fractions and decimals. Okay? And that's what I talked about an independent, dependent on that one. That's okay. Okay? And discrete has to be whole numbers and integers. Okay? So continuous, you can have portions of it. Continuous is going to be like gallons and miles and time, whereas discrete is going to be chairs or tables or people or books or anything like that. So you can have negative and still be discrete, but it has to be that it's going to be a whole number. And where that makes a difference is when you go to graph it. If I have a continuous, so if I look at discrete and continuous, if I have a continuous, which is what this situation was with the gallons of water and the pool and the minutes, continuous does not have an E on it. Oh my gosh. Continuous. Okay? If it is continuous, okay, your graph is going to look like this. We have minutes over here, we have gallons here, and it's going to be a graph that looks like this. It can be a line because I can have a portion of a minute. I can have a portion of anything. Whereas if I'm talking tables and chairs, okay, and I have tables here because my chairs are dependent on how many tables, okay, I cannot have a portion of a table. So these are going to be dots. This is a discrete graph. This one is discrete because it's going to be whole numbers, whereas this one's continuous. It can be a continuous line. It doesn't stop. One way to remember continuous is you don't pick up your pencil. You can just keep on making it. Where discrete, you have to keep on picking up that pencil. So in your book on example number 2, I'm on page 50, it talks about domain and range, and it wants to talk about a reasonable one, and we're going to explain. We're also going to talk about independent and dependent, because I'm going to be using those words. These are vocabulary words you need to know when I talk about them what they mean. Okay, so make sure you know you can understand. If not, please ask. So we have the first situation. A bowler pays $2.75 per game. Okay, which one depends on what? Does the cost depend on the game or the game depend on the cost? Well, actually the game will determine the cost. So the game is the X value. It is the independent variable. Okay, and that's going to be our domain. Our domain is going to be the number of games. Now think about that. I can have 0 games. Can I have a half of a game? No. So it's going to go 0, 1, 2, okay? And that's going to go until, I don't know, maybe they're having a marathon bowling night, and it's going to go that you're going to do bowling all night. But these are going to be whole numbers. Now, the range can be money. And it's going to be a multiple of $2.75 because you're going to have to pay one for each game. So $2.75. And then whatever $2.75 is, I'll do it. $5.50. And this one's going to go, and they're going to all be multiples of $2.75. Okay? We're not going to write them all out. Now, this one has to be, this one, whoops, that says numbers. Your domain here is going to be discrete. If your domain is discrete, everything's going to be discrete. Okay, you can't have, even though dollars and cents you can have portions of, the domain, it has to be whole numbers. So when I would go to graph this, if my domain is, if this is the number of games, I would have to have dots. Now your money could have a whole bunch of decimals, okay? Good. Look at B. Now, again, if you're doing this from home, you can just click on this. It won't give you the explanation of why, but it will give you the correct answer. So that's the reason the explanation of why is kind of handy. But a car travels 25 miles using gallons of gas. So it's going to be miles per gallon. So that means that gallons are going to determine how far you can drive. So gallons would be my independent, that would be my domain, and the miles would be my range. My miles are dependent on how much gas I have. Okay, so what can my domain be? How many gallons can I have? I can have 0, I can have a half a gallon. So this one, if I would be describing it, would be whole numbers starting at 0. Okay, my range is going to be starting at 1. Okay, I can go a half mile. Actually, that can just be, these are going to be all real numbers. But they're going to be positive real numbers, because I'm not going to have a negative gallon of gas, a negative miles, okay? So this one would be continuous because I could draw a line because I can have fractions and decimals. Good. Is a relation a function? In order to be a function, it has to have a one-to-one correspondence. No x values can repeat. So let's look at our x values. Do any of those repeat? Nope. So yes, this is a function. What if I would give you this? I know this isn't in your book, but I'd give you the ordered pairs 2, 5, 3, 5, 7, 5. Is this a function? Well, look at your x values. Do any of those repeat? No, they don't. So yes, that is a function. Okay? Another one. 2, 3. 3, 5. 2, 10. Okay? Do any of my x values repeat? Yes, they do. Now, the other, so they repeat. I have 2 2s. So no, this is not a function. Another way you can do this is if I have a graph. So I could plot these points. And what we would find out, so this one would be obvious, okay? You're just going to plot points, yeah, it's fine. But if I look at this one right here, if I go 2 and 3, and I go 3 and 5, and I go 2 and 10, we have what's called the vertical line test. And what the vertical line says is it says that you can draw a vertical line wherever you darn well please and find out if it passes through the graph. Okay, if it hits the point more than once, then it is not a function. So right here, see right here, I can draw a line and it only touches once. But if I draw a line here, it touches 2 points at that same time. So this one is not a function because it fails the vertical line test. Okay, so vertical line test is draw a vertical line. Let me try this again. A vertical line cannot touch more than 1 point at a time. That's that one-to-one correspondence. I have to have exactly one x to go with exactly one y. But here's the really interesting thing. Let me show you another graph. If I have this graph right here, and here's my graph, Okay, there's that horizontal line. Okay, draw a vertical line. Let's draw some vertical lines here. Okay. Do I touch it more than once? 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 No, this is a function. Oops, you can't see that. This is a function. And if I would write the set of ordered pairs, let's make this 1, 2, 3, 4. This would be 0, 4. It would be -1, 4. It would be this right up here. That would be a vertical line. Good. Okay, is this relation a function? If so, is it 1 to 1 or not 1 to 1? Okay, so if it's not 1 to 1, it's not a function. Okay, so here we go. On these, I'm always this is what's called a mapping, if they ever refer to a mapping. Sometimes they'll call it just a diagram. But a mapping, and what I do with this if I get a little confused, this says 1 goes with 17. And 2 goes with 17. And then I have 3 and 11. And I have 4. Hello. I have 4 and 10. And I have 5 and 10. Okay? Do any of my x values repeat? No. So, that's the reason it's going to work. Now, if I would have a mapping that would have also had 3 going to 10, well, then I would have had 3 going to 10. So, therefore, that one wouldn't have worked. Notice I made up my own little problem here. Okay, I made up my own little one. I added that one in. If it goes to the same number, so look at this. If one x value or one domain goes to 2 different numbers, that's not a function. This is what I do because I want to be sure, so I write it out. And notice that should have been on the last slide. Okay, now you get to try it in your book. Is this a function? Is it a relation? Is each relation a function? If so, is it a 1 to 1 or not 1 to 1? What? Okay, so on this one, we have -2 and 5, 3 and 6, 3 and 7, 4 and 8. Is this a function? No. So this is not a function. It can't be 1 to 1. Now on this one, we're going to do our vertical line test. So I'm going to do a vertical line. Do I touch the equation? Do I touch the graph more than once at any particular time? Now each vertical line gets 1 touch. Okay? Can intersect once. If it's more than once, it's not. So see how each vertical line only touches the graph once? So yes, this is a function. So therefore it's 1 to 1. The diagram shows shipping charges as a function of the weight of several online orders based on the situation. What constraints, if any, are on the domain of the function? Okay, so think about weight. And we're going to ship it. What do I know? Well, my weight, my domain, has to start at 0. But notice there's decimals, so it can be real numbers. So real numbers, 0 or higher. What constraints, if any? 0. Now, eventually you would have constraints. We don't know what those are because you can't ship a 1-ton thing possibly and worry about the money like this. So that's the reason we're talking about, is there one? And if you want a different or a more mathematical, wonderful one, go out and use that interactive reader. Margaret has a monthly clothes budget of $50. She maps the amount of money she spends each month to the number of items of clothing she buys. What constraints are on the domain? What constraints? Okay, so the domain is the money. The number of items, that's your range. That would be your range. The money is your domain. So what's her constraints? Can she spend $? Nope. Okay, that's not okay. You have to start at 0, but what can she go to? She can only go to $50. That's all she can spend. So that's going to limit, of course, her amount of clothes. Again, if you want to find the exact mathematical, perfectly worded, problem and answer, go out and watch the interactive, go through the interactive book. So a function is a relationship in which there's exactly one input for one output. In other words, no x values can be the same. The domain, that's your x values, your range is your y value. Why do we have to define it? Because it really does make a difference. We can't have unreasonable domains. We can't have negative numbers if we're talking about how many people are going to be alive, because we don't want to even do that, okay? We're not going to go there. Bad example, okay? So you get the idea. Maya is tracking the amount of rainfall during a storm. Describe the domain. What would the domain look like? What would the range look like? Okay? So, rainfall. Can it be a fraction? Yes, it can be. Can it be a negative amount? Not when it's falling. It's during a storm. So we're going to go 0, and we're going to go on up. It can be real numbers. That means I can have fractions and decimals. Therefore, it is continuous. Continuous. Okay? And then we're going to talk about, she's tracking it. Probably range would be your time. So your time can also be continuous. So it's going to go from 0 to whenever the storm ends. Okay? And that would be hours. So yes, that could be a discrete. This one would also be continuous. Because it can be a fraction. So this would be real numbers. What can you conclude about the domain and the range of a relation if a vertical line at x equals 5 passes through 2 points, 1 point, no points? Okay. What can you conclude? Well, think about a vertical line, people. Think vertical line. You know what it looks like. Here's a vertical line. And it's x equals 5. 1, 2, 3, 4, 5. Okay, what's my domain? Well, it doesn't matter what my x values are. They're just going to be 5. That's my whole domain. Okay, it doesn't matter how many points it passes through. That's my whole domain. Even if I don't pass through any points, which is a whole bunch over here. My domain is 5. That's all I can plug in. What's my range? It is everything. Okay, it's all real numbers. It can hit everything. Good. Okay, so the other thing it wanted us to talk about is look at this. Is this a function? No, it fails so miserably because look, if you do the vertical line test on that, doesn't it hit every single point? Yeah, so it fails the vertical line test. Okay, fails the vertical line test because it hits it all over the place. So this is not a function. And also, my domain is 5, 5, 5, 5, so it repeats all the time. I hope you'll read this problem to yourself and think about it on your own first. Philippe states that every relation is a function, but not every function is a relation. Think about it. There's a mistake. Yes, because the mistake is that every function is a relation. But we will have lots of relations that are not functions, okay? We have all kinds of relations, and we have a small amount that are functions. There's a more contained set there. This one is a great question, and we need to look at it. So we're going to talk about domain first. Domain are the x values. So if I'm looking at my x values, here's an x value right here. That's -4. Here's my next x value. That's -2. And I'm just going to go from left to right because then I'm going to go smallest to largest. Then we have a -1. And then we hit over here at 3. Those are the domains. Okay? Look at the range. Your range are your y values. So let's get rid of those x values, that x stuff. Your range are your y values. Start down here at the bottom. Here's a y value, no y value. Here's a y value, here's a y value, here's a y value. So what are my y values? -2, 0, 1, and 2. So you have to domain, you have to look this direction. So if I'm looking for domain, I'm looking here. Okay? If I'm looking for range, I'm looking at the y values, so look at the y values. Okay, now that we've done that, is this a function, people? Does it pass the vertical line test? No. Look at it, it fails right there. And there goes my hand, making all kinds of other things. Right here, fails the vertical line test. It hits 2 points at once. Oh, gosh, it fails twice. Woohoo, not a function. Not. I don't know what that word is. Not a function. Good. You're going to write out the domain and the range. Write out the domain. Okay, here's my domain. I like to sometimes kind of underline it. It'd be better if I underlined it. So here's my domain, my domain, my domain, my domain. Now, some books are really picky. Some teachers are really picky that you put this from smallest to largest. Some are like, yeah, whatever. It's just write down the numbers. So what I like to do is I like to always be sure of myself. So I'm going to put them in lowest, from lowest to highest, just to make sure if I have a picky instructor. So I have 1, I have 2, I have 3, I have 5, I have another 5. Oh, I have 2 x values that are all the same. So is it a function? Not a function. Now I'm not done writing my domain and range, but it's like, wait a second, 2 x values are the same. That means it's not a function. Okay, now, because I have 2 5s, though, I don't write them both down. I only write one of them. So I just write 1 5, and then I have a 7, and I have an 8. If I'm writing the domain, if I'm writing the relation, I have to write down every coordinate. But if I'm just giving the domain, I'm telling you 5 is part of the domain. It just happens to repeat itself. Now the range. The range, also let's go smallest to largest. It looks like it's a 2, and then a 3, and then a 4, 5, 6, 7, 8, and 9. Let's count and make sure. 1, 2, 3, 4, 5, 6, 7. None of those repeated. 1, 2, 3, 4, 5, 6, 7. We've got them all. Okay? And we've already answered that next question because when we went through and found out our domain, we noticed that we had 2 x values that are the same. Each day, Jacob records the number of laps and the distance he walks in miles on a track. Graph the relation and whether the distance that Jacob walks is a function of the number of laps. Okay, here we go. First thing we have to decide is which one is the x and which one is the y. So just look at your x and y's. Okay, look at that. What does the 3 stand for? And what does the 0.7 stand for? Well, do we ever walk 0.7 of a lap and record it? No. So this is your laps. And this is your miles. Okay? And the other way you probably could have figured this out is miles per lap. Okay, miles per lap. So now we're going to plot those points. So let's pause and plot those points. Go. One thing to notice is notice that my x value goes 1, 2, 3, 4. And here I'm going to go 0 and then I go all the way to 1. So each one of these is 0.25. Yes? Okay, good. Go back to graphing. Okay, so when you plotted the points, this is what it looks like, right? Now, why did I just plot points? Why did I not draw a line? Because you might be going, but wait, I have decimals over here. Yeah, but am I going to talk about a portion of a lap? Not too often. So if they ever talk about a portion of a lap, but note all your x values are whole numbers. So they're talking about whole laps. They're not talking about a portion of a lap. So that's the reason we're going to leave it with dots, because this one would be discrete because our laps are going to be whole numbers according to the problem that is given to us. Now, is this a function? That's what they're asking. So take and do your vertical line test. I hit it once, I hit it once, I hit it once, I hit it once, once. So yes, this is a function. Here's how you can also check. Look at your x values. Did any of those repeat? Any of your x values repeat? Nope. So that's the other reason. Okay, you get to go do homework now. If you have questions, you know where to find us. Thank you.